So, bonjour. Let me try to. So I thought, since it was a while ago and I rushed it a little bit, so I will go back just one step and explain this principal part business once more, and then that I was doing at the end of last time. And then hopefully that will finish in one lecture, and then I will go to sort of this, the nuclear bomb of calculation devices, which is the equivariant theory and localization principles. So that's a little more difficult in the sense that then it's not covered by the text, so then I will switch to some other thing. Okay, so today I hope I'll start this localization story. But just first also, so to put us back in the framework, I also just want to remind you how difficult this thing is in some sense. So you remember what I was discussing last time is the singular element or singular elements of families of hypersurfaces. So of hypersurfaces. And now I will, from the beginning, I will do this slightly more general setup because the naive one that I described in detail last time only works for projective space. So the idea is the following, that you have X, let's it be projective and dimensional. But of course, in the background, the basic example you always think about is this. Right? So, and then you will assume that this X is endowed by a line bundle, which is, of course, here you can think of this as O of D on Pn. So here, the sections of the line bundle are just the degree D homogeneous polynomials in n+1 variables. But in the more general situation is this, and this does arise. I mean, it could be a Grassmannian with a line bundle, and you want to understand something about families of hypersurfaces of the Grassmannian. There's lots of problems when this arises. So this is just a special case, but it's really this one that we looked at last time, and I want to remind you what the general one looks like. Okay, so then the question, more or less, Bertini's theorem says the following is that, so now I will do hypersurfaces in X. So I will look at, so there's two notations, right? So one can look at H0 of L, but just a little, it's a little shorter. I'll just write gamma L. It's the same thing. It's the space of sections of L. And then the idea is that generically, so the generic element here so then I'll denote by, say, Y sub F, which is just the part where this section of the line is 0. So in our example, it's just you take a degree D polynomial, it takes its 0 set, then Y is smooth. So that's what Bertini's theorem says. And now, what will be interesting is what the singular part is. So so what I suggested last time is a little bit of cheating, but let's describe the singular part. So how do you describe a singular hypersurface? Well, what I say is that let's say F is singular at some point P in X, and we do the really naive thing, which is that we take this polynomial F, we write down local coordinates. So we write down X, little x1, etc., xn these are local coordinates at near P. And we write down, then we also trivialize this line bundle N locally near P is just, so we also trivialize L. So locally it will, now locally near the point P, this F looks just like a function. And then we write down F in this way, right? F near P is just the sum, you can write it this way, alpha to the I, x to the I, so where this I is a multi-index. So I'll maybe give you an example. So let's just do so that it's the smallest non-trivial case. So let's just do, say, n equals 2. So you have 2 dimensions. So then you only have 2 coordinates, x1 and x2. And of course, then locally, F just looks like, so there is alpha empty when there is nothing going on. Then you have alpha 1 x1 plus alpha 2 x2 plus, and then these are the linear parts. And then you have, well, I can put here a little p here just to say that these are the coefficients near P. So this is just a little symbol that tells us it's near P. And then you do have the quadratic ones, and there is 3 of those. And then I just put the multi-index, I put 1, 1 here, and then it's x1, x2, plus alpha 2, 2, 0 of x1 squared plus alpha 0 to x2 squared. This is the quadratic part, and then it goes on. So this is the description, and now these are our coefficients. So now what does it mean that f is singular at P? It means that the partial derivatives are all vanish, so that, and the partial derivatives exactly are given by this formula. So a way to say that is that from f, I can describe a thingy like this, an f upper 1, the first jet of f, which is locally is just described as by these 3 coefficients. Okay, and I'll put a little piece here. And so now I can say that f is singular if f, so now this is at P, f1 at P is equal to 0, right, as a vector. So this is now a vector value thing, 3 things. If all 3 of them vanish, that's when this is a singular point. Okay? Now, of course, I simplified my life here because I, didn't explain precisely, this conversion. I just said, well, in the local coordinates, this is what it looks like. But of course, we have to do this somehow globally. So to do it globally, then the following thing happens. So yeah, maybe just before I go on, this already tells me something. By the way, this looks a little stupid, in fact. I mean, if you think about it, what we're doing here, but this little stupid is necessary because it seems like I take a section of a line bundle, if you like, I take a polynomial. I already know, obviously, if I know the values of this polynomial at every point P, in other words, if I know alpha, the value of f at P is this alpha empty P, that's the constant term. The rest is 0, of course, at P. So, of course, once you know the section, you already know, as you know the section at every point, obviously you know the section. So it looks like this thing where and some more coefficients actually somewhat superfluous. To say it otherwise, suppose I only know, this is a rank 3 bundle, so it seems like it contains more information. But actually, obviously, if at every point I know the value of the section, I will also know the derivatives at every point, right? So somehow there is some little strange thing, but yeah, just keep that push that in the back of your head and forget about it for now. But this little strange thing is there. Nevertheless, it turns out that everything works out nicely. Okay, so I want to understand this, and so Well, let's first just do this global thing, what we are trying to calculate. So I said singular elements, blah, blah, blah. What are we talking about? We are talking about the following thing. So we are trying to understand that if I take P of gamma L, so the projectivized set of sections, so these are more or less the set of subvarieties YF, right? So this is just this. Set of all of these, then you can think of that as a projectivized space of sections. Then so then what sort of a condition is, and so if you like, if I take now cross X, so then in here you have, so this is our usual double diagram. In here you have the pairs where there is a point. So if you like here, you have this d tilde, which is just Fp. So F is a section up to, now I think of it as up to a constant. So that's normal. So these are these pairs where F is singular at P, right? So, and I explained what that means here now, in local coordinates at least. Okay, and so one of my point is that the condition, this condition that's described here is simply the vanishing of three numbers. So for n equals 2, in general, obviously, it's going to be the vanishing of n plus 1 numbers. So this is of codimension n plus 1 in general, right? So this is n equals 2 here. And so what really interests us is the discriminant, which means that, if you like, it's the projection of d tilde. So it's the projection of d tilde onto the first coordinate here, or you can also describe it as just the space of F such that F is singular at least at one point. Right? Because what does it mean, a singular hypersurface? It means that there is a point where it's singular. But you see now this is seems a little more difficult to see what it is. But at least now what I would like to say now is just what the codimension of this is. This is now codimension 1. Right? It's because it was codimension n plus 1 here. This now it's a little. This d tilde was codimension n plus 1. And but now in this product, so this is n-dimensional. When I project it, it will just remain codimension 1. Okay. So what the picture is that you have this kind of crazy big projective space, and then here you have a codimension 1D. It's called the discriminant, and then you would like to understand its degree, basically. So when I say what the problem we are trying to solve is the degree, and so the question is, the real question more precisely for me is the degree of D as a subvariety in this projective space. Oh, sorry, question. This is now a little too. Okay. So this is what we're trying to calculate. And so now I explained this again, but just a little rushed last time. I'm just repeating, it was a while ago, is that, so and how do you calculate the degree? Well, the idea is that generically the way you calculate the degree, so this is it's a codimension 1 subvariety, and then you just look at a nice line here, which is just a little copy of P1, a line, and calculate the number of intersection points. Okay? Okay. So what we are interested in, again, is the following. So a question more precisely, I'm just repeating the same thing, is that I look at a pencil of elements. So I look at an F and a G, and reasonably I'll assume that they are both smooth, for example. That's enough. So such that YF YG smooth. And I'm looking at this thing. So if you like, I would like to understand the number of T0, T1 such that T0F plus T1G, so this is now an element in P1, right, is singular. Okay? And so now we have a condition for that, and it's singular if this is true. So this is the most important thing here, that I gave a condition for what it means to be singular. And so that just means the following. And so now I do this little cheating, which is the following, that I will calculate actually all, instead of this, assuming that knowing that the generic singular hypersurface, I sort of explained this last time by this projection, has only one singular point, this will be the same thing as the number of just singular points which could appear. Okay, so this is just the number of points P in X. So this is the trick, really. So this is the second important thing, such that there exists a T0, T1 in P1 where this is true. Okay. So this is kind of, this is a triviality in a sense, but it's also, I changed the picture completely, right? So here I was counting points on projective line, and now I'm counting points in X. But so the logic is simple. It just says that since a generic hypersurface that will appear has only one singular point, so it's enough if I count this total number of singular points in the pencil at any place. Because you see, each point here, each T0, T1 here, will only have one singular point, and that singular point is counted here. So these two numbers are the same. But this changes things dramatically, because now I'm calculating really some intersection theory in X, which is in a sense is much simpler. And so now comes the part which I will not, it's sort of a technical thing. Intuitive is somewhat clear, but anyway, this I will not require a precise derivation of. So what are we talking about here finally? And so this is then the following. I can also write, now I just rewrite it that way. So there exists a T0, T1 in P1 such that T0 of F1 plus T is, it's a linear thing, T1 of G1 at P is 0. At P. I mean, I could have put P, maybe I'll just put it this way. So that's, of course, the same thing. I just use that condition, okay? All right, and now what is this thing? That's actually kind of amusing. It's just the same thing, of course, as the number of points in X where, so what does this mean that there exists a point? It just means that these two vectors are collinear, right? So that F1 P is parallel to G1 P. And now this looks very good. So I'm sort of explaining what I did, but much more detail for a general X, okay? Because, of course, the question is now what this thing is finally. And so here comes this principal part, which maybe I'll denote this way. So the point is that this F1 of P is locally is just a vector valued function. Of course, globally, as usual, it's a section of some vector bundle. And that vector bundle is called the principal part. So now that I have this perfect description from our point of view, it's just a Chern class. Maybe I can even, no. So the idea is that F1 of P, if invariantly, consider this is just a section of the principal the principal parts of functions with or sections of L. Okay, so because this is some vector bundle, so now we don't have to worry for a second. So this is this principal L is some vector bundle of, and in this case, so we know what the number of it's a vector value with n plus 1 elements. So this is at least we know here that that the rank is equal to n plus 1. So the rank of this vector bundle. This is just some ordinary vector bundle. Okay? And so why we like this is because if I take a vector bundle of rank n plus 1, and I'm asking the question of the number of points in a variety. So this, of course, G is also, so G is also the same. So F, sorry, maybe I should have, excuse me, so just G, sorry, and there's no P here. Sorry. Okay, so erase this. This was not right. What I meant is that F1 and G1, both of them are sections of that thing, of some vector bundle, which at locally is just an element of that vector. Okay, so now the point is that if I have a rank n plus 1 vector bundle, I'm asking when two sections are linearly dependent. That's the top minus 1, if you remember, CL of V is the cycle that some gamma 1 gamma R minus L plus 1 sections, generic sections, are linearly dependent. Right? So here V is rank R. So this is just a reminder. So that was the condition. So if you substitute now here, the rank is n plus 1, and you want 2, so R, so you want R minus, so you want n plus 1 minus L plus 1 to be equal to, you want 2 of them, right? So that, no. Yes? Yeah. And so for this, you want L to be L equals N. Okay? So the condition, this condition, so I can continue now here, sorry. So this was all just observation, but you can continue. Now this is actually equal to Cn of Pr1L. So this is our first final calculation. Of course, since x is, well, this is just as well, since x is n-dimensional, this will give us a finite number of points, and this number of points now is the answer. What we're looking for. It means that in a general family, general pencil of sections of this line bundle, there will be this many singular elements. And so then the second part was, so this is one story, and of course now you can see very well that I can extend this now to the next thing easily. So I can also talk about triple points now. So I can just, this now perfectly works. We don't have to worry about triple points. So this thing is called, this singularity is called a double point. I don't know why. Well, anyway. So the triple point is just the next case. So in case of triple points, you have the same story, but now you want, so you look at f of 2 now, and f, so this will be all of the alphas that I wrote down, but now up to degree 2, so you will have just alpha. So this is for n equals 2. I'm explaining so that it's clear. So here you have alpha 1, alpha 2, and then you have alpha 1, 1, alpha 2, 0, and alpha 0, 2. So you'll have 6 elements: 1, 2, 3, 4, 5, 6. All of these again at some point P in those local coordinates. So it's the same picture. And then again, it's a definition, you say that this F gamma L has a, or rather, you say that YF, the variety that it defines, has a triple point, at P if F2 P equals 0. F2 at P equals 0. Okay? So it's the same, it's complete analogy. Before F1, P was 0, now F2. So that means that every, derivative up to degree 2 vanishes. That's what a triple point is. Okay, and so you see that now you repeat the whole thing. So now it's a codimension 6. It was codimension n plus 1. So now it's going to be much worse. So now let me just do it for n equals 2 now. Okay, so I'm not going to do the general case now, just n equals 2. Then this is a codimension 6 condition. So you can do the same thing now. You can take P, the same picture, gamma L cross X. But now you have 6 things have to vanish. So you have this D tilde 2, which is codimension 6. And then you have in P gamma L, you will have this D, which is the projection. So it's identical. It's just replace 1 by 2. D tilde 2, which is that there's a triple point at least at some point. So YF has triple point somewhere. Right, it's the same thing as before. And now this will be, so this was codimension 6, and this one subtracts from codimension 2 because X is 2-dimensional. That's what I'm looking at. In general, the calculation is somewhat different. So this is codimension, how many? 4. Right, so it was 6, and then you have to subtract 2 because now you projected, from you deducted 2 dimensions from X. Okay, so it's codimension 4. And so when I ask the same question, I go back here. Now I'll have, instead of this, I'll have, so everything's identical. So you just repeat this whole thing, so I'm not going to do that. Just the only number you need to change, well, these ones you need to change to 2s. And then same story with linear dependence and all that. So the question then, I just repeat the question. The question is, you want to know, so now it's 4, so instead of a pencil, I need to take a 4, the P4 thing, right? So I'll take F0, F4, and then I'm asking some generic smooth things, and I'm asking for the number of elements T0, T4 such that the sum of Ti, Fi has a triple point. Has a triple point. So if you like Y, but it's I right? So I'm asking that. Now that's the question. Now it's codimension 4, so this is some number. I want to calculate it. And the answer, so you repeat precisely what it is, so I'm not going to repeat all those logic. It's the same thing that this thing is going to be. And so I'll just do it for n equals 2. Otherwise, there is some function of n that you have to write. But anyway, I mean, it's easy to see what it is. But anyway, it has, in this case, it's the same story. It has to be Cn. So here it says C2. So this is just n equals 2. C2 of this principal part 2 of L, right? Same logic. Each of these F's will give a section of this bundle, and you will need a linear. What does this mean? It precisely means that it's linearly dependent, and then you just do these calculations. So you have n plus 1 minus L plus 1 needs to be equal to 4, and n is 2. So anyway, you calculate and you get the answer. And it turns out to be 2. So this is rank 6, right? Okay. So that's sort of one, it shows how our tricks with Chern class, etc. work. And then the second part, which you've done some exercises, if you did what I posted on Monday, is that you want to, of course, calculate this now. And in fact, so calculating these is, the first step is very easy, but then it's not very easy anymore. Okay, so now the question, how to calculate this. So Chern classes, C of PR, say M, even in general, of L. Okay, so actually it's not so difficult at the beginning, and that actually completely solves the problem for the projective space, but for other x's, this is not so easy. So the key equations are the following. So if you like, you can also think of just, so now I'm going to this calculational mode, right? How to calculate the thing. So, well, just one little remark is that, of course, very naturally, you could think of the previous thing that if I look Fp0, so the zero jet is just F itself. So you can think of, I didn't introduce this, but of course F0 is just F itself, right? So if you take the zero jet, so you just take the coefficient, and then this will not be here, and it's just alpha 0p. The constant term is precisely what F is, okay? So there's a natural logic in that. And one thing so now we want to invariantly define this. So what this means, I mean, so this is a part I'm sort of going to skip. Maybe I give you an exercise for this, but, well, now it's F2, but think about just F1. So to understand what vector bundle this is, what you need to do is just to change your chart and then to understand how these things change, right? And that's some annoying work that I don't want to waste time on now. So intuitively, this is fairly clear what's happening. I mean, one thing that's completely clear, and so this is what I want to say. So one fixed point for us is that if I know, for example, F1, so if I know the function up to degree 1, then I definitely know the function up to degree 0. I mean, I know its constant term. I know what it is. Okay, so gives me, so F1 sort of gives F0. So what I mean by this, that in fact, more precisely, what I have is that I have a map from the first principal part into just the 0th principal part, which is just L. So there's definitely a map like this. I know what that is. I know, if I know the principal, linear principal part of function, I also know the value of the function. That's clear. And so then the question is what this is, and this is the part I don't want to spend time on now. But the claim is that this is simply the cotangent bundle of the, so this is an exact sequence like this of bundles. This is an n plus, remember this is an n plus 1. So the ranks are, this is n plus 1, and this is 1. It's a line bundle. Okay? So that the kernel is simply the cotangent bundle. As it's not so surprising, because if you think about it, what is happening is that here you have these coefficients, x1, x2. So these are linear functions locally, sort of linear functions on the manifold up to degree 1. So that's precisely sort of what a cotangent bundle should be. So it's not surprising. But I don't want to get into the some precise local calculation for this. Okay, it's not difficult. There's in algebraic, one reason is because to me, unfortunately, what people do in algebraic geometry is not so natural, and so I can just do it in differential geometry and just show how, as I said, I mean, you have these x's, you can change coordinates, and I can show you what's happening precisely, and the change of variables of this kernel will be precisely the same as for the cotangent bundle with the differential of the change. So you can just do that, and you see. Yes, sorry, yes, you should, we should, yeah. Okay, sorry. Now you have to tensor with L. Sorry, I always forget that. because it's with values. So the x is cotangent map, but the values of the x's are in this L, and so you have to put that there. Sorry. So in algebraic geometry, of course, they don't do that, and so this is just a funny or important technical point, because you don't actually have locally affine coordinates necessarily. So that makes it very difficult compared to differential geometry. Differential geometry, you can always take a point manifold and just assume that locally it's Cn. In a sense, here locally you don't have that. I mean, there are manifolds. Most manifolds actually don't even have curves in them. So if so this is a conjecture, like the Green-Griffiths conjectures. If you have like a high degree hypersurface, then even if you map C in there, just even holomorphically, actually, no, I mean, if you map C in there, then that map has to be constant or has to be in some subvariety. So in any case, you don't have local coordinates. That's the point in algebraic geometry. So that makes it a little more iffy. So you have to look this ideal, you divide by the ideal sheaf thing for this cotangent bundle, which to me is, well, I'm not an algebraic geometry, it's a little difficult to comprehend. So anyway, I mean, basically you have to use always the implicit function theorem instead of just having local coordinates, and that somehow is very annoying somehow to me. So that's also why I'm not doing this. So not because I'm lazy, because I don't know how, sort of, you see, in a way. Anyway, so let's accept this fact intuitively, it's clear. But then, of course, then I can use Whitney's formula, and I see precisely what's happening. I mean, by Whitney, the total Chern class of this bundle, P1, is simply the sum of these Chern classes. So it's just a product of these two, if you like. So it's C of the total current Chern class, PR1 of L, is just simply C of, if you like, is of a direct. So I can replace, this is not a direct sum. That's why its bundle is difficult. But for the purpose of Chern classes, I can just think of it as a direct sum, and then it's just this. Or, yeah. So if you like, I can even write it this way. I can write this as C of, if you like, L tensor, and then I just have O plus T star X. And so this is true. Okay, so I converted at least this PR, which was kind of this strange bundle, we didn't even know what it is, now to some bundles that we perfectly know what it is. And so now, in particular, we can calculate it now if X is Pn, and this is what I did last time, then we seem to be very lucky. Then we can just, we know that there is a similar bundle. There is a map of O of 1 to the power n plus 1. So we've done this calculation many times. This is Tx, right? And this is O, something like that. So there is, we have this sequence there. This is comes from the, remember, it's the same, this thing is equivalent to this thing that Tx is equal to Hom SQ in my language, the way I like to write it. So, where this S is the universal subbundle, as Q is the universal quotient bundle. If you look at this formula, immediately applies this. Okay, so this is O. This is O, and this is an exact sequence. And this exact sequence is very helpful because, of course, you can see that this is now almost we're almost there because this is giving me something. So what does this say? So what it says is that say the Chern class, so I apply the same principle to this exact sequence. To this one, these two are almost the same. So L over D in this case. So, yeah. So what should I do? So this means that C of Tx, say plus O, is the same as C of, oh, sorry. So when I say n plus 1, of course, I mean direct sum n plus 1. So n plus 1 copies, right? So this is a vector bundle of rank n plus 1. That's the book what uses that. It's a little confusing. I hope that not too confusing here. So O of 1 n plus 1, right? So then I just tensor everything with and dualize, because that's what I need. I need to, so I almost have this. I just dualize this, so then C of, so what I do, T star X, a T star, sorry, it's not X now, it's Pn now. Plus O, so it's just the dual of this, so it's just going to be minus 1 there, but I still need to tensor this with O of D. So this will be then C of, and then now I look at this thing, O of 1. This sum is just O of minus 1 now, right? So it's just going to be O of minus 1 and plus 1. And then I will tensor this with O of D. So I hope this is not too confusing. This n plus 1 is not a power. It's a direct sum of, so it's like this. When I write n plus 1, it always means like that. Right? So it's an n plus 1 full thing. So it's n plus 1 copies of O minus 1, and I tensor with D. Because this is what I want. I want L, this is O of D. I want O plus T star X. So here's T star Pn plus O, and this is what I want. Okay? So, and this is obviously then the same thing as C of O of D minus 1. So each factor is multiplied by O of D power n plus 1. Right? So this is a sum, really. You can write it. This is O minus 1, direct sum O minus 1, n plus 1 times, and this is multiplied by O of D. Right? So you multiply each factor by O of D, so you get O of D minus 1 and n plus 1 times. Okay, and for this now, this is easy, since the multiplicativity, Whitney, etc., this is just, so O of D minus 1, so C of O of D minus 1 to the power n plus 1. Now it's a real power now instead of a sum, because the sum of bundles goes into the product. And so, and this is now just a line bundle, so this is just 1 plus D minus 1 times Xi to the power n plus 1. And remember, we need the nth Chern class. This was the original thing. So Cn of per 1 of O of D, so this is over Pn now, O of D, thus is equal to the coefficient of Xi to the n in here. And so if you calculate that, that just works out to be, so the top is n plus 1, so the previous one is n plus 1 so it's going to be n plus 1 times n plus 1 times D minus 1 to the power n or something like that. Okay. N plus 1 times D minus 1 to the power n. I think that's the correct answer. Yeah. Right? It's, if you take psi by Newton's formula, you have n plus, yeah. And just the last thing before I stop, I want to finish this, is that you can, of course, it turns out that you have a similar formula. So this, I'm not going to finish the calculation. This will be an exercise, but just a similar formula in general. You have PRM goes to PRL. PRM minus 1 L. Sorry. PRM L So just I did this for m equals 1, but it's true in general. PRM minus 1, and the kernel here is just the symmetric, the mth symmetric product, tensor product of T star of this bundle T star. This didn't cut, sorry. So anyway, you have hopefully space left of this formula that you just wrote down, so I'm just going to write it so that it's visible. So by induction, you can calculate the same way all the high ones, so you can also calculate the triple points this way. Okay, now it's actually correct. Okay. Okay, so that's the break, and so then from here you can do the same calculation for the next case when you want to calculate, say, F2. Okay, so as I said, this is now we write somewhere, so we got some really nice conversion of some enumerative problems to Chern class calculations. And we discover, of course, that we can only calculate these Chern classes for projective space, because there we have this strange thing that we identified the Chow groups completely, and then we can just play with that. So the question is, okay, so what do you do in general? And this is what we're going to do now. Okay. So let's go on. Okay. All right, so let's just start anew. So as I told you, this will be sort of the magic wand of enumerative geometry, which is localization formulas. And so this then will bring us to also various interesting questions, algebraic combinatorics. But so today I will just start this, so I will explain, not localization, but just equivariant theory. But I think in some other courses you have equivariant cohomology, I can imagine, no? No. Okay, very good. Okay, so I will not explain, so it's good to see this from various points of view. So I thought you have it some other place, but if not, anyway, I'll do something self-contained. So the idea is the following. So we will now endow, our varieties will be endowed with a group action. So and the idea is the following. You have a group G. So this is a group. So examples, in fact, it turns out that for what we're doing, we just need very simple groups. I mean, the groups you should think about, there should be linear groups, but so example could be, the more complicated one could be just GLN. You know what GLN is? Everyone knows what GLN is? Okay. GLN, or it could be just, GL1, you know, that's just C star. So if you look over the complex numbers, and sometimes I might take just the diagonal elements of GLN. So maybe it could be just T equals C star to some power, say I'll denote by G also, okay? So by the way, for this part of the course, there'll be some other notes. So this is not in the Harris-Eisenbud book. For some reason, well, I think it's considered to be more advanced. But since we are doing perpendicular mathematics, it's not, for us, different things are advanced. So, so now this is what groups are. You know what groups are, so you multiply, right? So that's fine. But now, and then there are group actions, and I suppose you also know what that means. So we will have some X. It could be just some smooth variety. And then we say there's an action. Then we say, well, G acts on X. So that's just a map like this, where, you know, denote it this way, right? And where's the basic thing you need is the associativity. So that just says that, so the property is that GHX equal to GHX, right? So that's what an action is. Okay. So our purpose is to describe now the equivariant Chow groups. That's for today, more or less. That's what.
What do you require this action in terms of this map? Does it have to be continuous?
Well, it's in our category. So this is because this is a product variety now. So it has to be a morphism of varieties. And you want this from it because it's a group, so this is meaningful, right? I think this is enough, more or less. That's what an action is. Okay, actually, before I do equivariant Chow group, let me just talk a little bit about maybe some examples. So actually, for our purposes, this group C star will be perfectly enough for most things that we're going to be doing. So this is not, the group part is not so difficult, but so, I mean, the simplest thing is, so C star, for example, the action, maybe just a notation, so I'll often do this silly notation like this, so C star acts on say, Cn. So, but that's just a notation for this. Okay, so what is the action? So this, you can take a linear action. So here the parameter I usually denote by t, and then I will have, so this will be the formula for the action. I take here some vector x1, xn, and then, so now the point is, in a certain sense, the most general action will look like this. We need to achieve this situation that this G times H thing, this action has to be multiplicative, right? So you have to have a formula like this, T to some, say, A1, X1, T, A2, X2, etc. T, N, no, T, A, N, X, N. Okay, so I'm describing this map now. I take an element of the group. That will be a non-zero complex number. I take an element of X, which is now just a vector with n components, and I tell you what the action is. So now the point is, what I'm trying to say, that in a certain, it's not completely true like this, but in a certain sense this is necessary. Certainly, if say it's only one component, it's necessary that this T should be to some power. So because you want this multiplicative, so you want a map, some C star to say C star, where G, it's a homomorphism, basically. And so if you have a linear action, this is necessary for some A1, AN integers. Okay, so these, these are now just integers. These are called exponents, so these are called weights. So more generally, well, let me just do it for 2. If you have, I can extend this example slightly. Let's G be now just C star cross C star. And let's do the same thing. Let's X to be again Vn, Cn. And let's do sort of this diagonal action, but which still satisfy this. Then you just have the following thing. So you'll have St now, so you have 2 elements, and then you have this X of the group, and then you have again n vectors. And this will go to, and so here now we'll have 2 numbers, so it will be S to the power, say, A1 times T to the power some B1. So you can have different integers now to have this homomorphism. So what I'm saying is that if you just look at, say, one of them, if you want diagonal actions, that it's easy to see that T going to this number here has to be a homomorphism, a group homomorphism. That's what this says. And so the only group homomorphism C star to C star are the power functions, and that's why you have to have this thing. Okay, anyway. So x1, and then you have s to the power an, t to the power bn, xn, okay? For some, so this is now I'm giving you examples. For some, now ai, bi, now in z squared, so pairs of integers. Okay? So this is now examples of actions on vector spaces. Now just this is terminology. These are called the weights. Of the torus action. Yeah, maybe I should have said something else before, but anyway, I'll say it now. The point is that this is actually general. So in fact, what is true is that let's take a commutative group. So let's T to be just C star to the power G. And let's take, so this is not necessary here, but I only looked at these situations and let T x equals Cn be linear action. So that means that each action is a linear map, so preserve the linear structure in Cn, or put it differently, you can also say that T, this is given by a homomorphism, a group homomorphism from T to GLN, which is the set of all linear maps. So, okay. Okay, so in this situation, then the idea is there exists weights well, now I had this G thing, so now okay. No, just a second, I don't want to screw up the notation. Yeah, that's lambda. Well, I didn't prepare this notation-wise, so let's just be nu 1, nu n in, nu n, yes, in zg. These are weights. So it's similar to this, right? The weight of a group with two components is a two-component vector. If you have a torus, this is incorrect, this is little g. And you have a group with g components, then the weights, each of the weights will be of g elements, and this is analogous form, which I'm not going to write down. But there exist weights and vectors in this vector space v1, n in Cn, non-zero vectors, such that, in fact, in this basis, you have this diagonal action. So this is actual theorem. You need to prove that in representation theory, but we'll just assume this. So such that, in fact, T acting, so now T is sort of a vector. T acting on some Vi is equal to just T to the power, T will be now an element of this torus. T to the power nu I Vi. Okay, so this is what you see here. This here, in this case, I just assume that the basis is a standard basis. Then if you just take the vector v1, say, which is just 1, 0, 0, 0, 0. So in this case, you see that, say, ST acting on the vector 1, 0, 0, 0. So this is v1, is precisely going to be just SA1, B1, SA1, T, B1, S to the power A1, T to the power B1 of this vector V1. Right? So this is precisely the form, but now for OVI. And this notation, T to the new I, well, the I is just equal to, so in fact, T has coordinates, T1 up to TG. And then this is, again, a homomorphism from here to C star. So this is just T1 goes to, and so you look at the corresponding component. So this is the problem with this notation. So you have new I. So you have new I1, etc., new I. So those are the components of that vector. Okay? And it's a product. And so the idea is, again, going back here, this will be an important thing from all purposes, that whenever you have a torus group, say with G components, and a linear action of this torus group on an n-dimensional vector space, then these are classified up to the Churchill basis by what's called weights. Weights are just these vectors, like that was the example here, and this is the formula, okay? Okay. So, well, that's one example of actions. I mean, of course, now these are not so interesting for us. We want more things with where x is projective, but so this immediately gives us an action. So for example, if, well, let me just, so that I don't have this notational problem, go back to the situation when t is C star. If I take this linear action, can be converted to an action, a projective space. So x is Pn minus 1, and you have these numbers A1. So these weights then are just integers. Then I can define an action projective space this way. So this is just T acting on x0, xn. Sorry, so this will be 0. Sorry, like that. And it's a little easier. So I take a point in n-dimensional projective field from 0 to n. Then it's just going to be the usual action that inherits from t to the power a0 of x0 all the way until t to the power an xn. Okay, so, and it's clearly well defined. Okay, so this is now a more interesting action. In particular, it's more interesting. Let's look at the, say, one thing that will be important for us is the following. So fixed points. And this is the following. So you have this t acting on x, say. This actually, for some reason, fixed points are only interesting if the group is commutative for some reason. Okay? Then we can define, yeah, it's the beginning is a little boring, I'm sorry. Xt to be just all the points in x which are fixed by the entire group. So now I can write Tp, right? This is a new point in x. Tp is equal to p for all elements of the group. So these are the fixed points. So let's just look at a quick example. So let's look at, say, C star acting on P1. This is sort of the first interesting thing. So you have to be a little careful here. I mean, you'd be tempted to just take T acting on x0, x1, by writing that it's just tx0 and tx1, right? So that looks like a simple thing I can do, but we know that this action is actually trivial, right? Since this point is the same as that point. Okay, so this is not interesting. Let's just look at the situation when you take one of the weights is +1 and the other is -1. Then you get something non-trivial. And so what are the fixed points? So now P1, T. So I prefer, if it's possible, if I know which group, I'll just write T here. So T is, but T is C star now. Okay. So what are the fixed points here?
1, 0, and 0.
So it's just 1, 0, and 0, 1. That's when you can just rescale them back. Otherwise, it's not true. So it's the 2 points 1, 0, and 0, 1. Okay. This will be very important eventually. Okay. So what else did I forget? Fixed points. Yeah. No, I think now I can get to the main point. So this is equivariant Chow groups. Well, I think technically it's kind of simple in a sense, but to imagine it is not so simple. So the idea is the following, that when T acts on X, what I'd like to express is, so it's we'll call A, say, well, I'll call the group G now so that it's in complete generality. So what I'll instead of, so we have this AIX, which we know they are the Chow groups, which are defined by subvarieties, right? So now when I have an action G acting on X, then I'll define a new thing that's called equivariant Chow groups, where I put a G there, okay? And the sort of the logic of this thing, what I would like to do is that I'd like to take X divided by T. So I would like to take the quotient of X with respect to T and take its Chow group. That's sort of the idea behind this. Okay. So it's clear what, well, in principle, we know what X mod T is. You understand this? So it just means that these are orbit spaces, sort of. So you take an equivalence relation on X. The 2 points are equivalent if they're related by an action of a group element. That's what equivalence is. The problem is that this object is just very bad. In many ways, it's very bad, actually, which I will not even get into right now. But the point is, but in any case, it doesn't express what we want. But one case when it certainly should work, and then it's true. So let's just give an example. Well, there's a very simple thing that you can do. You can just take X to be the group T, sorry, I promised G and now it's T. Sorry, so it's G. There's only one group now. G. Basically, when I write T for the group, that means it's a torus group, that is C star to the power G. When I write the general one, it could be more general. So the example when X is G and the action is just the product. So you take, and the action is that you just take G acting on some element H. So this is now in the group and this is now in X, and it's just GH. Okay, so there's an obvious action when a group acts on itself. So in this case, it's quite clear what X mod G should be, right? So the equivalence is complete and obvious, and it's just a point, so nothing is left. You factor the group out by itself. The equivalence relation, in a unique fashion, just gives you the thing. So in this case, here, in a very natural way, X mod G is just equal to point. And so then a thing is going to be true. Then it's just so G of G is just going to be equal to A of a point. So this is easy. So this is sort of an example of what we are trying to do now. And unfortunately, already a seemingly much more trivial thing, when I have x, which is a point now, is much more complicated. So the case x equal a point is much more complicated. And this is what I'm going to be discussing now. Because, well, it's true that, of course, when you divide, it's still a point, the classes are a point, but now the equivalence has extra structure somehow, because the whole group, there are many elements that bring you to one thing to another, right? So the great thing here is that for each, when you do this equivalence, for each pair of elements in X, there's a unique G that brings it the one element to the other. In the case of a point, this is not true. And we want to account for that. Sort of that's the idea. So I just want to remind you one thing, because it's... So one thing is just that if you take the Chow groups of, say, AI of AN, so sorry, this is CN, it's the same thing, right? And then these were just Z if I equals N and 0 otherwise, right? So this is true. And so the other thing which follows obviously from the definition is that if you look at AI of X, and then you compare this to AI to some subset of X where you throw away a little part, then these things should be equal if say, the dimension of Y is less than I. Because, right, if you take what are these? You remember, these are just given by some subvarieties, and these subvarieties are, you see both in X minus Y and X if the dimension is much smaller than the dimension of subvarieties you're looking at. So this is not so surprising. Okay, so now comes the difficult definition. Well, difficult. It's the following. So what I want to do, this was important, I want basically free actions. So this action is called free. So this is, so here, this. So this is a free action. So you understand what a free action is, right? It just means that the map from T, if you take a point, TP is injective. So, so if you restrict this thing to, sorry, G X, mapping into capital X is injective. That's what we want. And so I want that. I want to just emulate this stupid example that I had here when I have a free action. And so the way we do that is that we push this up. So now we multiply by a piece of AN, and then we take a subset. So what we are going to do is that we will look at the following thing. So I'll take X, and I will multiply it by some set. You can assume it's actually one of these linear things. So you just multiply it by some subset, some V. So V is a vector space, base, rank L, and with a T action, with a G action. And now what I will do is that inside this thing, I'll look at U in G, U in V, is going to be an open set with restricted to which the action is free, on which the G action is free, and where the codimension of V minus U is large. Okay. So this is the setup. So let me go back here and just repeat this here. This is the important part. So again, what I'm doing is I start, so just the setups have X, G acting on X. And now to define what I want to define, I do the following. I look at this, whatever is described there in that thing. And now the point is that if you, so clearly the Chow group of X cross V, see this thing will be just push, this will be the same thing, it will just push up the so if you have a cycle in X, then in X cross V you'll just have the cycle of X cross V. Basically just you'll have sort of an add to each cycle and multiplication by V, by n-dimensional thing. So this is just maybe the other way around, sorry. So a generalization of this formula is that if you take this is the Chow groups of AN, generalization, and if you have now the Chow group X, you multiply it by V, then it just pushes up each cycle by N. That's clear, because if you had some cycle Z, here you just take Z cross V, and now it's that many dimensional higher. Okay? This is now just a parenthetic remark, so that you to motivate what I'm going to tell you. I'm just going to give you a precise thing. So if you combine this idea with this idea here, then you can say the following thing. You can consider simply X cross U now, okay, and you divide this by G. And the point is that here the action is free. So note, this action is free. Because if it's already free on U, that was the thing that I supposed, so the action is going to be free. And so as a result, I can sort of use this logic of saying that I will define the equivariant, the ith equivariant Chow group of X simply as the Chow group of this quotient. Okay? But so now I have to, and this is why I was telling you all these things, I have to correct. And the correction is the following, that because of this push-up thing, I will push the thing up by so now I assumed what? The rank of V was L, so this L. So the things get pushed up by L, and then you subtract the dimension of the group. G is the dimension of the group. Okay. All right, so that's the main definition of the thing. So again, what we are doing is, in order to understand what this is, to have an analogous thing, we multiply X by something, well, really something on which G acts freely, and which doesn't have too much Chow group, because so this is where this logic is. I mean, V only has a Chow group in dimension n, and then you throw something out, but the codimension, what you throw out, is large, and it's not going to influence thus well. Okay.
Freeness of the action is enough to know that the quotient is nice?
actually, no, actually no. So you need something that's called proper action. So this is, I'm cheating a little bit. Okay. But so for this, pardon?
So you wrote this as it's independent of it.
Yeah, no, that's what I wanted to say next. So of course now, I mean, so I said E is large, so if it's sufficiently large, I mean, it's easy to see. It follows from this remark that I made here, how large it needs to be. Then actually it's a theorem, which I'm not going to prove, theorem, that this thing is independent of this definition is independent of this pair UV, which I'm using. Okay, now actually in the examples that I'm telling you, so it's a very good question in fact, it will be completely clear that what the quotient is, so what you need to do. Okay, so let's see the example and then we continue next time. So this is kind of a little bit difficult part. Maybe just one convention. So there, as I said, the logic is that you push up by this L because of this situation, and then you have to subtract with a group because you divide, there's division by the group, which is a free action. So that's the logic of this shift here.
Okay. You mean it's both independent of U and V, or?
Of this pair, I meant. Of this extra data that I introduced.
What do you mean by a large codimension?
So it's just, it will be sufficiently large so that using this principle, you can check that obviously, just let's even fix V and I vary U. Then using that principle, you'll see that some of the, so we have a U1 and a U2, say, and I want to say that it doesn't depend on which one I chose here, even for a fixed V. Okay? So then Ui plus L minus G will not change if the dimension of, so I just didn't calculate it, but it's just some concrete number. If what I throw away, so this V minus U that I throw away, right? So if I throw away has a smaller dimension than I plus L minus G. So if I take two U1s and U2s where the difference between V minus U1, so I have some spaces. So if the dimension of V minus U1 and V minus U2 is less than this number, I plus L minus G, then this thing is well defined, right? That's what that thing says. And so that's what I mean by sufficiently large. Okay. Yeah, well, I'll just have enough time for my example then. Okay, so let's do the simplest example, and then you will see how this works. Just one thing before I go on that, well, you will see actually in the example, but actually the Chow indices now can be negative. So one thing, of course, now AIG can be non-zero. It may be non-zero for I negative. You'll see that in a second, so it's different from that. So when you divide, this can happen. And the other thing that I want to say is just a definition. The definition is identical to what we had before for the Chow cohomology, whatever, I forget what that thing was called, when you put the index upstairs. So we just define AIG of X as, well, as a n minus I g of X, where n, so I'll use, okay? Now let's just get to let's just get to our most basic example already. So this is the case example, say, as I said, this is already pretty interesting if you just have C star, and that's kind of strange, yes, and then X is just a point. Okay, so then the action is obviously well defined. This is already quite interesting. Okay, so what happens then? So let's see. Well, here, and now this somewhat answers your question about what kind of actions we're looking at, because it's sufficient to control the action on U, and in all of our torus group cases, the action is completely clear what you can choose. So here I'll just choose V to be just Cn, and I'll choose the weights to be just 1, 1, right? So that means that Tx1 xn is just going to equal to Tx1 Txn. Right, so this fits into what I was doing at the beginning, but with all those AIs now are just equal to 1. Okay? So first of all, so now let's find our U. So what is our U where this thing acts freely? So this is where finally you will see what's going on.
The subset where all the coordinates are non-zero?
No, that's not, that would be bad, because then the codimension of the difference would be 1, and I want it to be large, right? But it's quite clear that actually you can just take it to be V minus the origin. I mean, on the origin, it doesn't act freely, but if you have at least one non-zero coordinate, then the action will already be free, see? So now we don't have this projective space thing, it's just vectors. So here, this is invariant. It also has to be invariant, of course. I mean, that goes without saying. Is T invariant? I didn't write that, but that's necessary, and the action is free. And it's proper in that sense that, of course, we know the quotient is, of course, U divided by T is just P. Well, actually, I used N. I apologize. I promised it's going to be L, so I go back. I'm sorry. It's L, because I use N for the varieties dimension, so this auxiliary will be L. Okay, I have one more. All right. Okay, and now let's do a little calculation. So actually, you will see that the good notion is this one. So let me start here. So then, say upper I, T of the point is equal to. So first I just go to this definition. It's n minus I, but n is 0 now. So now you see it's minus I of the point. Okay. Yeah, then I haven't done anything yet. And now I'm doing the thing, which is I'm going to this definition, and I go, so now the dimension is L, this G is 1 now, right? So this is just equal to I plus L minus 1 of PL minus 1. Okay. What did I do? Minus I. Yeah, I would have been in big trouble if I don't have that. And now I'm going to do something else, and you will see why this works out nicely, and all this pushing up and down thing. Because now I'm going to convert this in our usual sense to the cohomology. So look what happens. This is L minus 1 dimensional. So this is just equal to AI of PL minus 1. So AI torus point is actually AI PL minus 1, which of course we know what this is. This is just Z times zeta to the I, right, in our Chow group business.
For example, we take another weights, will we change somehow this calculation? I mean,
well, I don't want to change. So the only thing is that then it's not free, the action. That's what changes. because you will have some -1 will act trivially. That's the problem. Yeah, that's a good question. Okay, but this is it, and so I finished because I ran out of time already. So I just want to make some remarks, and we'll continue from here. So first of all, what you see here is that we see the stabilization. We see the stabilization. So what I mean is the independence of UV. So this story, right? So, and it's even seen how this happens. So you start increasing P to the L minus 1. Of course, if I is larger than L, then this does not work. So it obviously depends on L, but if you choose L large enough, the codimension of U, so the codimension, I didn't write that here. So here the codimension of V minus U is equal to L, right? Because it's a point. We only throw away the point here. It's here, sorry. So you see what you need. I mean, you see why you precisely need. But you also see that if I let L to be infinity, so the codimension is large, then this AI stabilizes. It becomes a fixed thing. So it's the thing that had before. And the other thing that we actually have a nice answer. And in fact, it turns out that thing is a group. And I'm not going to prove this, but it's sort of intuitive. It's clear here that this upper I is again an algebra. So there is an intersection product. So this AI, well, it's just observe. We observe. It's not a proof. That this A upper thing, so I take the direct sum, T of a point, is actually just Z. It's simpler than we had before. It's just going to be, as you go to infinity, you let L go to infinity, obviously you'll just get the polynomial ring in one variable. And so, right, so if you take sort of the limit of this thing, then the product stabilizes also. So you take this as a ring, you take the product, and you let L go to infinity. This product, then, if for L large enough, does not depend this thing. And you actually have a simpler thing than before. You get sort of a P infinity, an infinite dimensional projective space whose Chow group is this thing. Okay, so yeah. And then I'll explain more next time how to use this. But the main point is that amazingly you can reduce. So our problem with the Chow group calculation was that we could only calculate in projective space, or maybe Grassmannians, where we had this Totaro theorem of identification, essentially only there. If you take a general variety, then there were no tools. What this will give you is reduces, in fact, reduces the calculation to this space, to point divided by group, to P infinity. So that will be for any variety on which I have a torus action, of course.